CLion, a cross-platform IDE for C and C++. Download now.
Hello everybody, welcome. I am Lieven and I'm going to talk a little bit about coroutines today. This talk initially takes 90 minutes, so we're going to reduce it to 1 hour and we'll see how far we're going to get in the presentation. But later on I will share the full slides and I will also share a link of a video on ACCU of this talk. So coroutines, a feature from C++20, one of the big four, and actually what we wanted was a nice finished polished closet. However, what we got was kind of this, an IKEA build it yourself set. So that's what we're gonna do. We're gonna build up the stuff, a lot of boilerplates, and we're going to try to understand what that boilerplate is, and if possible, we can get rid of it in the future. But before that, I want to talk a little bit about concurrency versus parallelism. You can see we see two drawings on the screen. The left-hand side is concurrency. Two things are happening, chopping and stirring, but none of them happen at the same time. So we chop a little bit, we stir a little bit, and both tasks, chopping and stirring, in the end are having progress. If, however, the chopping and stirring would happen at the very same time, then we talk about parallelism. And as you see, for this parallelism, we need two cooks or we need two cores. Now, let's go back in time. The MS-DOS operating system. You could launch an application. For example, I'm launching my text editor, and the only thing I could do was editing text. If next I wanted to play a game, for example, Outrun, I was forced to shut down the text editor and then launch the game. And if I wanted to go to text editing again, I had to shut down the game. So it was not even concurrency because we had to quit something completely. And then, for example, Windows 3.11, Windows 95 came into play, and I could have several applications running at the same time. I could edit text in my Word editor, and I could see in the system tray the clock ticking, and I could also open up a game like Minesweeper. We had the impression that all those applications were running at the same time. They were not. It was again concurrency, and the operating system was handing out CPU time to the different applications, to the different processes. So it was still at a very big level of processes. So it was swapping from one process to another. Later on, multi-threading came into play. So within the same process, within a given application, multiple threads could be running. So I could have an application where I fill in some data and I press a button which started a calculation which could take a lot of time, but nevertheless, we could see that the user interface of the application remained responsive. I could press the cancel button, I could press the abort button. And that was thanks to multiple threads running. There was a thread running the calculation, and there was a thread running the event loop of the user interface. Again, at those days, when Windows 95 came out, that was a Pentium, that was still a single core, meaning it was concurrency. Within the application, within a process, the CPU and the operating system could hand out time slices to thread 1 of application A and thread 2 of application A, and of course also to threads of other processes. So it was already a bit more fine-grained. It was not swapping between processes only. We could only also swap between threads of the same application. And the moment multi-core came into play, it's well possible that thread A, one of process A, and thread one of process B were running at the very same time and we had parallelism. Or thread 1 of process A and thread 2 of process A were running at the same time. Now, coroutines are taking this to a next level of much more fine-grained, as we will see. We can have multiple coroutines running at the same time in a concurrent way. So CPU will run a bit of coroutine A, then a bit of coroutine B, then again a bit of coroutine A. And it could be possible they run in parallel, that coroutine A is running on core 1 and coroutine B is running on core 2. So coroutines is taking, let's say, the time slicing of the CPU to a much more fine-grained level. Okay, what's the difference between a function and a coroutine? A function, we can start it and it will end. For the coroutine, the same things apply. However, it has two extra features. The coroutine can suspend itself midway. And later on, we can resume that coroutine and it will pick up where it left off. Something that a regular function can't do. A regular function, you start it, it runs till the end. The final statement or an early out, that's all possible, but when it returns, it has finished. So a basic flow of coroutines is we have a caller C, which starts the coroutine. The coroutine does some processing, and then it suspends and hands over control back to the caller. The caller himself is then doing some stuff and says, now I'm going to resume the coroutine. Coroutine again does some action, still it decides to suspend itself again. So an important thing here is the caller and the coroutine are collaborating. They choose to grant one another CPU time. The caller and the coroutine can run on the same thread. They can run on different threads, but nothing is saying that the coroutine is running on a different thread. By default, it will run on the same thread as the caller. It is possible if a coroutine suspends, like in this drawing, that it's returning control back to the caller, but it can also give control to somewhere else, not the original caller. In this talk, we will not see any examples of this, but it is well possible. Okay, when is a function considered a coroutine? So let's say we have a function foo, it takes some arguments, it has a body, it has some return value. We don't care about the type at this moment. When does it become a coroutine? The moment in the body one of the following three keywords appears: co-return, co-yield, co-await. From that moment, that function is a coroutine, and the compiler will treat it as a coroutine and the magic will happen. As we will see, in order for the magic to happen, we will have to aid the compiler a little bit. And that's why we are going to look at the coroutine from two different angles. We're going to look at it from the compiler perspective, but we're also going to have a look from the user perspective. And we're going to analyze the UX side of that. And the UX side, that's where improvement is needed towards the future. And for that purpose, we're going to start with a first example. What we are going to do, we are going to model a radio station. When we construct the radio station, we're going to tell it what kind of music we would like to hear and how many songs we would like to hear. And from that moment on, when it's constructed, a radio station comes alive and it can play songs. And we are going to model that by a coroutine. When there is a new song ready to be played, the coroutine will yield that new song and then it will suspend. As a user, I can listen to that song, and then when it has finished, I'm going to tell the coroutine, could you please resume and prepare the next song I want to listen to. We have a song database is of less interested with the two types of music and the songs which are present and from which it will select. Now, imagine we would write this as a regular function. We have two arguments. The style of music I want. I can choose between rap music or electronic music, and how many songs I want to listen to. We implement this with a stupid for loop, and listening or having the music ready, that's printing to cout. Now, in this case, we will see that the function starts, does everything at once and then ends, meaning we get all songs at the same time. That's not what we want. So that's where the coroutine will help us and give us the behavior we want, because with a regular function, we don't get it. Now, when that coroutine is there, it's going to result in something. And in the textbooks, different names are being used for that. Some people call it the coroutine interface, some call it the coroutine API, the coroutine remote control. Actually, whatever you want to call it, it doesn't matter. But it is something we want to interact with further on. We want to ask for the next song, aka coroutine, could you please resume? We want to check if there are still more songs, because if they are all being played, resumption doesn't make sense anymore. And at some moment, we want to stop and we want to go home. So everything needs to be cleaned up. We don't want to leak anything. So this is not the behavior of a regular function. This sounds more like it's some kind of an object. And we can interact with the object. Please resume. Is there still more stuff to do? So this coroutine will have to result in some sort of object for us, the user, to interact with. This coroutine has state. It needs to know what kind of music we selected. It needs to know how many songs we have requested. And we have seen in this for loop, we had an index from 0 till the number of songs -1. It will need to know how far the index has already progressed in that for loop. Because when it gets suspended and resumed, it needs all of that information. And it's for that purpose that the stack frame is going to be stored on the heap, as we will see later. Because there are stackless and stack-full coroutines, C++20 brings us stackless coroutines. Now, let's go back to the notion of a stack frame. When a regular function is calling another function, some stuff is happening. The return address of the call is put on a stack so that when the called function ends, it knows where to go back to. If the called function has a return value, a placeholder is put in place on the stack where the called function then can fill in the value. And if the called function has arguments, all those function call arguments are put on the stack. And once we are inside the called functions, we can have local variables. They are also put on the stack. And then the called function returns. And all of the above is cleaned up, as if it was never there. It's obvious this will not work for a coroutine, because when it suspends and we would clean up the stack, we lose all our valuable information. So the stack frame of the coroutine cannot just be removed, it needs to be put aside. So when a resumption happens, it can be put back and we can continue where we left off. So that's why it's typically stored on the heap. Sometimes compilers can optimize this heap usage away. But if we put something on the heap, it means we need to clean it up at the correct time. And that is the responsibility of the programmer. This is not being done automatically. So we know about new and delete, and we can have memory leaks. That has been solved by smart pointers. But here, this problem is coming back. The stack frame of the coroutine is on the heap, and it's up to us to clean it up at the appropriate time. So the stack frame gets put in some allocated memory on the heap, and we are getting a pointer to it. A handle is the correct terminology. And it's up to us to hold on to that handle and to destroy it at the correct time. Okay, let's write our radio station function that we saw before now as a coroutine. We still see the same for loop, but where we used to see out the song, we are now saying we are co-yielding the song. This means it's now a coroutine because we used one of the three keywords. We use co-yield, and co-yield means at this moment the coroutine is going to give back, is going to yield the value, and will typically suspend. We also see that our original function had a void return. Here we are returning a radio station. We have no clue what that radio station looks like at the moment, but that's that coroutine object, the coroutine API, coroutine interface. And another thing we can question is what happens when we hit the closing curly brace? That's the spot where normally a function returns. So this one is kind of returning nothing, but the coroutine can at the closing brace return something. Well, actually co-return something. One of those three keywords. So basically, we are saying when we hit the closing brace, we are returning nothing, or maybe something. But from the signature, we see we also return the coroutine object. So we are kind of returning two things. We will see later on what's the difference and how it works. Okay, that radio station. Let's look at it from the user perspective. We're going to create it. So a constructor will be called. We won't be calling the destructor ourselves. The compiler is going to do that. However, that radio station class that emerges, it's up to us to destroy it, either by having it going out of scope or whatever. We want to ask to the radio stations, are you done? Are there still songs for me to listen to? At a given moment, we're going to say, hey, radio station, next song, please, as if we are pressing the next button on a CD player, which we should not call when the radio station has played everything we asked for. So, pressing next, prepare or give me the next song, that's resuming the coroutine. And coroutines have a feature, maybe we could call it some sort of scope creep. Did we need it? If we create our radio station, does it immediately play a song? Yes or no? Or when we create a radio station, all what happens is the DJ is coming with his pile of records and he's sitting ready till we say, yes, please play the next song, and only then he puts the record on the turntable. In case the radio station would immediately broadcast a song, we say it's eager. If it's not, it's lazy. Eager versus lazy, that's a feature of a coroutine. In our example, we will go for lazy. Okay, next song, and are we done? We can combine this together in one method in our API next song. One method less in our radio station API, easier to understand. If next song returns true, that means there is more. If it returns false, it means we're done. So after we resume the coroutine, by saying next song. Next song is the equivalent of resume. We will only get signaled if there is something more or not. We didn't get the song yet, so we will need to explicitly fetch our new song. We know there is a new song because next song returned true. It's on the turntable and we can listen to it by explicitly fetching it and printing it out. That's our equivalent of listening to the song. So at the application, the user level, it looks like this. Hey, I want a radio station of music type 0 and I want 7 songs. The coroutine returns the coroutine object of some type. We don't care about it. We use auto. And then we say, please resume, next song. There is something there. You still have a song. Okay, I'm going to fetch it. I'm listening to it. And on my radio station, I call value for that. Naming is hard. We will see later on what that value actually does. But that's then giving us the value generated by the coroutine. And at a given moment, next song is saying there is nothing more. The coroutine has ended and we fall out of our while loop. So when we look at this, we see that using a coroutine is not that hard. Looks simple. Now, let's switch and look at it from the compiler perspective. The compiler is generating, computing values. It's going to come up with a song, which we will see will be modeled by an std string. So the compiler will need to store that somewhere. I have a value for you. Where do I store this? We have seen the feature of a coroutine. Should it start eager or lazy? That's a configuration aspect of the coroutine. The coroutine has many configuration aspects. We can say it should suspend at startup, meaning it's going to be lazy. We can also configure how it should behave at the end. Should it suspend at the end or not? What if an exception occurs in the coroutine? The compiler wants to know what should happen. And as said, we are not creating that radio station ourselves. The compiler is going to call the constructor of that. How can the compiler do that? We will have to tell the compiler how this is done. Now, all these configuration things, that's done in the promise type. The promise type, as we will see, is a simple struct, and it needs to adhere to the promise type concept. The promise type concept is defining a bunch of functions that we should implement as member methods on that promise type struct, but not in all cases we need to implement all of those. Most of the time we only need a subset. The promise type concept has nothing to do with std promise, just to avoid confusion. Now, the configuration of what should happen at startup. In the promise type, we need to implement a function initial suspend for that purpose. Return value auto, we don't care about what that is at this moment. And if it should suspend at startup, aka lazy, we return suspend always. If we say, no, go ahead, immediately start playing a song, we say return suspend never. Same thing for the final suspend. Suspend always or suspend never. By implementing initial suspend and final suspend, we have already provided the compiler with information of how we want the configuration at startup and at the end. Okay, what should it do if an exception occurs within the coroutine body? For that purpose, we need to implement the unhandled exception method in the promise type. At this moment, let's not do something special. We expect our coroutine to never throw, and if it happens, well, the shit has hit the fan. Let's just terminate. Now, the current state of our promise type, we have configured it by implementing 3 methods. It's rather trivial. This is not science. Okay. If the coroutine hits the closing brace, it's returning something. Either it's returning void or a value. We will see an example of that later on. And that's also something we need to tell the compiler. In the promise type, we either need to tell it, again by implementing a function, we are returning void, or we are returning a value. Our radio station is at the end not returning anything, so we need to implement return void. Well, what could we do when we don't want to return anything? Well, nothing. So the empty function is sufficient. Open brace, close brace. So current state of our knowledge of the promise type, we have configured it, what it should do at startup, at the end. If something goes terribly wrong, an exception is thrown, and we are not returning anything at the end, so I'm telling you. Okay. Now, midways, we saw our coroutine is generating a value. It's coming up with a song. So for that purpose, the compiler needs to be able to store that value. It's going to store it in the promise type. So we have been using the promise type to configure it with a few methods by now. There was no state yet. Now we are adding state to the promise type so that the compiler is able to store in that promise type the generated value. And we will also tell it the moment it has generated that value if it should suspend, yes or no. Our goal was to suspend, but there might be cases that we say, no, you should not suspend. In our example, we will suspend. So for that purpose, we need to implement a function called yield value that takes a const reference of the type we are generating. And again, we are returning something of a type we don't care about yet, auto. So we are generating songs. Songs are in our model strings. So our yield value says a string value by reference is coming in. You know what? I'm going to store it in a member I called value of type std string. So my promise type now has one moment value. And when the compiler calls yield value with the value the coroutine has generated, we store it and then we say suspend always, like we have seen in initial suspend and final suspend. Suspend always. Our goal is to suspend. Okay, so the current state of knowledge at this moment, we have configured it for what to do at start, and if things go wrong, we are not returning anything, and we were able, if the coroutine comes up with the value, to store it in the promise type. It's in the promise type, it's for sure not yet at the user side. And there is one more method we need to implement for sure, and that's the getReturn object. That's the kind of like the factory function for the compiler so that our radio station really comes alive. We will come back to this shortly. Let's look at the hierarchy. We have our little promise type, which has, let's say, some configuration and also state. The promise type is stored in the coroutine handle. The coroutine handle, in the end, needs to be stored in our return object. The coroutine object, the coroutine API, aka our radio station class. Now, our radio station class is going to get that handle at constructor time. So it's not creating it. The compiler is creating that handle and is going to pass it on the moment it calls the constructor of our radio station. So that means the constructor of our radio station needs to get a handle. So that's an argument. The handle of a coroutine is templatized on the promise type. And that handle, that's really the core thing for the compiler. And since we are dealing with coroutines, it means that handle is going to have methods that don't come out of the blue. Resume. Is the coroutine done? This coroutine should be destroyed and all resources should be freed. Is there actually still a handle? And the promise type lives in the handle, so if I want to get hold of the promise type, handle, could you please give me the promise? So, let's see how we can already implement our radio station class. We have a struct promise type. That's the name it needs to have. It needs to be called promise type. And then we say a coroutine handle templatized on that promise type. Let's give it an alias name, coro handle. The radio station gets a handle at constructor time. We store it in our member, which is of type coro handle, as can be seen on line 25. And the destructor of our radio station, if there is a handle, we will destroy it. Okay, so we already have a few pieces of our radio station class. There is much more to come. Next song. That was one of the methods we came up with that we wanted to be on our radio station. Now, if there is no handle, or there is a handle and the handle says we're done, there is no next song. We return false. Otherwise, we call resume on that handle. The coroutine gets resumed. And at the end, we check if the coroutine is now done. Maybe it is. And in that case, we don't have a song and we return false. If it's not done, we say we have a song, return true. Okay, we implemented next song. Yeah, there is more, there is nothing more. Now we need to get our song out of the handle. Well, actually, in the handle lives the promise type, and that's where the compiler stored it. So, in order to get that real value, we say handle, please give me your promise type, and in the promise type we know the member is called .value. And our radio station now has a method that will return the song. Okay, final piece of the puzzle. Get return object is going to be called by the compiler to create our radio station. We know at constructor time it needs to pass a coroutine handle and potentially other constructor arguments. In our example, there are none. So we need to create a promise type. Then we need to create a coroutine handle in which the promise type is then going to sit. Then we create the real return object, our radio station, which gets at constructor time that created handle. And then this can be returned. Step 1 and 2 can be combined because the handle has a static factory method which is called from promise. So our coro handle from promise, we give this, start this because that's our promise instance. From promise gives us a handle. We pass this handle to a call of the radio station constructor, and that's what we return. We have implemented get return object. So let's put everything all together. Our radio station class, constructor and destructor. We don't want this to be copied. Next song we've seen the value to get the real value, the song out of it. Now, it all fits on one slide, so you cannot say that the radio station class is that hard. However, we still need the implementation of the promise type. That's yet another slide. Here we see everything put together. And this is then, let's say, the coroutine itself and the user of the coroutine. So basically this slide, that's what we would have liked to be the only thing we needed. Unfortunately, it's not. We had to implement a promise type. We had to write some boilerplate in our radio station, the coroutine object. Okay. We see we have a while loop over here. Now, we want an iterator. While loops are so passé, we want to use a range-based for loop. What does that mean, the range-based for loop, to work on that object radio? It means that object radio should provide some methods, begin and end, for example. And begin and end are going to give us iterators. Now, an iterator should be able to be advanced, so it needs the operator plus plus to increment it. And if you dereference an iterator, you get the value it is pointing to. And iterators need to be able to be compared, because you want to know, when I start from begin, plus plus, plus plus, did I reach the end? Am I equal to the end iterator? So an increment on the iterator actually means resume, and dereferencing the iterator actually means give me the value which is stored in the promise type. Now, we will implement this iterator type inside our radio station, and yeah, it's obvious we are going to need the handle and also the promise, because in the promise we know that's where the value lives, and we need the handle to say, yeah, you increment the iterator, meaning handle resume. Now in this iterator, let's store the handle at constructor type of the iterator, and when the coroutine is done, we could say in the iterator the handle should become the null pointer, for example. When the handle is the null pointer, it means we're at the end. Right. Makes sense. Okay. Our iterator gets at constructor time the handle. We store it in our member m handle. When somebody dereferences the iterator, we say, okay, handle, give me your promise. And then I fetch the value. When somebody increments the iterator, let's first check if there is still a handle, because otherwise we're done. If there is still a handle, we resume the coroutine. If now the coroutine would be done, we set the handle to the null pointer. Our iterators should be comparable thanks to C++20 and the spaceship operator, but the equality operator is sufficient here. We say, yeah, compiler, give me the default implementation, which is just comparing member by member. The handle is actually a pointer. Pointers can be compared, so default comparison is okay. So this is the implementation of our iterator. We said that the radio station should provide a begin and an end method, because that's what the range-based for loop is going to call. So how do we implement begin? If there is no handle, or it's done, we return an iterator with a null pointer. Otherwise, we create an iterator and we pass it our handle, and we already resume it, so that we can immediately dereference begin to have a value. Now, the end iterator, when you call the end method, it should return an iterator, which is the end iterator. Well, that's the iterator class constructed with the null pointer. Okay, let's already draw some conclusions. The coroutine function itself, that was rather easy. The code in main was also easy. The boilerplate concept, that was not rocket science. It was not that hard. It's annoying, we should deal with it. And we need to do this for every coroutine we will ever write. So, is this production ready? We have now seen how it works, so we are now the experts, right? But do our colleagues understand what this all means? Now, if things could just be a bit more simple in life. C++23 brought something to the table. which is called a generator. Now, actually, our radio station is a generator. It just generates strings. So in C++23, all the preceding slides can be collapsed to this one slide. Let's give an alias a generator of a string. We call it a radio station. We implement our coroutine radio station, which returns an std generator of std string, and we call coyield. That's it. No need to implement that radio station class. No need to implement a promise type. No need to implement an iterator. We get this for free. I think this is a huge improvement. Now, this is the only improvement that has arrived in C++23 related to coroutines. Not everything is a generator, unfortunately. Let's take a second example. Let's implement a pinball machine. Remember, coroutines, we said it's about collaboration. On a pinball machine, you could say, we are collaborating. I am playing, and the coroutine is the other player. So each we collaborate, each we take turn to play a ball. We are not returning anything. I do a bit of stuff, I play at the machine, the coroutine plays a bit at the machine. Once we lose our ball, we are not returning anything. We're not saying, hey, here's a string. No, there is nothing to return. The keyword we're going to use is coawait, so not coyield this time, but coawait. Note, maybe it never stops. The same with the generator. We saw before we were a generator of strings, but suppose you implement a Fibonacci generator, well, it never stops. It's endless. Of course, at a given moment, somebody says, yeah, I'm not going to resume you anymore. I have enough numbers. But the coroutine itself is actually never stopping. It has yielded, it has paused, and then somebody decides to never call it and destroy it. Okay. How would our coroutine interface, our coroutine API look like? Let's call our resume method play. Play a ball on the machine. There is no need for a getValue method, so yay, one function less to implement in the promise type, so that's good. And we will configure how many turns we are allowed to play. So that's the coroutine function argument. Using it at main, let's say we want a pinball game with 4 balls. As long as we can play, so there is still a ball, we play. The coroutine loops out of those turns, 1 to 4 in this case, and then it says, yeah, I am playing, and then it says coawait, suspend always. Remember, for coyield, we had to implement a yield value method that was storing a value and was then also saying suspend always. So coawait is very similar here as to the coyield. Both say, I want to suspend always. There can be other mechanisms here that it's not always suspending. We'll see if we get there. That's about awaitables. That might be just in time or just out of time for this talk. Okay. There is no yield value needed, so we can remove this method from the promise type. There is no state, so that member can also disappear. So it's more or less the same things as we have seen before. Initial suspend, yes. At the end, we also suspend. When we hit the terminating brace, the closing brace of the coroutine, we're still not returning anything, so return void. And if an exception would occur, okay, let's still terminate and get return object, our coro handle from promise. We create the handle, we pass the handle to the constructor of the pinball class, and then that is being returned. So the promise type looks very alike as the one we've seen before, a bit easier in this case. The pinball class, similar as before, at constructor time we get the handle, we store it at destructor. If the handle is still there, we destroy it. Play, aka next song, if there is still a handle and we are not done, we continue, we resume, and we check if we didn't end at this very moment due to this resumption or there is still more stuff. And there is no get value on this class needed at this moment because we don't fetch values. Now, can we cheat the system and avoid all this boilerplate in this case by using stud generator? I'm not saying this is a good idea, but is it possible? It is. Imagine we would return this pinball machine into a generator of int, and we don't call await, but we always call yield the value 0. Actually, nobody cares about this value. But at main, we can use a range-based for loop again, as long as there is something in the range-based for loop we are playing, and at the end, we're done. Okay, the value that we got returned was each time a 0 and we couldn't care less. So yes, we were able to implement this with the stud generator. If it's a good idea, I don't know. But it allowed us to avoid again all the boilerplate and have the same example fitting on one slide. Let's go to a third example. Suppose the coroutine is going to do some work and that work takes a lot of time, and that's why we want to slice it up. Let's say we want to calculate the average of a very large set of values, and per resumption the coroutine is going to add a few of those values, in our example only one, and after all the resumptions, or when sufficient resumptions have occurred and all the work is done, at that moment the coroutine can say, now I can divide my sum by the number of values, and at this moment I can return this value. So we are going to pause in the middle and not return anything. We already saw that's the co-await keyword. And this time at the end, we are going to return a value. And for that purpose, we return a value, we co-return a value. Of our object. The resume method, play, next song. This time, let's call it calculate. And this time we are going to return a value again. So our API needs again a method to retrieve that final outcome. Where will that compiler put the final outcome? We already know, we can guess. That will be in the promise type. Now, in our calculator class, let's call the method to retrieve it get result. So let's first look at main. We have a vector of numbers. We provide it to the coroutine. We get the coroutine object. As long as there is stuff to calculate, we loop. Of course, we print out stuff, but normally we would do some interesting stuff here, and we're collaborating, you a bit, me a bit, you a bit, me a bit. And when there is nothing more to do, when the coroutine has reached the end, then we say, coroutine, I would like that result, and print it out. On the coroutine side, how do we implement? We have a local variable sum. We're going to loop over those numbers. We add the current number to the sum, and then we say, co-await, I have nothing to return, co-await, and suspend always. When the loop is finished, we print out, haha, everything is calculated, and then we are co-returning our result, sum divided by the amount of numbers. Now, coroutine, main, both look simple again. But this time, we need an extra method in the promise type. At the end, the coroutine is co-returning a value, meaning the compiler needs to store that value in the promise type. So that means our promise type needs again state. And we have seen before in the previous examples, when you didn't have to return anything, we need to configure the promise type with a return void member method. Now this will be a return value member method. So return value, it's a bit similar as the yield value. The thing comes in as a const reference to the type it is. In our case, it's just an integer. We store it in a member in our promise type. We called it value. And that's it. The compiler is able to store it in a promise type. The only thing we need to do is fetch it in our average class, our method called getResult that says, hello, can I please have your promise and give me this value. Can we again implement this one with the generator? If it's a good idea, remains to be seen, but we can. Let's first look at the coroutine. We say it's a generator of an optional of int. In the loop, each time we add a number and we set co-await, we're now co-yielding an empty optional. As long as we are busy, we are returning empty optional. And when we hit the end, when everything is finished, we return an optional containing the value. Again, co-yield, not co-return, co-yield, because that's what a generator does. It yields stuff. Then we look at main. Okay, so we have again the range-based for loop. Remember, std generator gives us iterators for free. What does it return? An optional of an int. So on line 33, we're checking, is there something in the optional? If so, we print it out. Now, this would also mean that if we loop again, the loop would end anyway, because we also could have written a break at line 35, but we know those things are aligned. And if they are not, somebody wrote a big bug. If there is nothing yet, so if the optional being checked at line 33 is still empty, we loop, and on line 31, the range base for goes to the next item. So again, we can avoid the boilerplate by using std generator. If it's a good idea, that's up for debate. Okay, 7 minutes left. Awaiters. Let's see what those are. An awaitable is the operand of co-await. We always saw co-await, blah, blah, blah. And the same for co-yield. And we saw in yield value, we stored the value, and then we also said something, blah, blah, blah. What's an awaiter? An awaiter is a specific way to implement an awaitable. And as the promise type was a configuration point, what to do at start, what to do at end, awaitables are another configuration point. And as I said, they are being used whenever co-await or co-yield is called. An awaiter has three methods: await ready, await suspend, and await resume. What are those? Await ready is called immediately before the coroutine is suspended. So a coroutine is about to suspend, and just before that, it calls on an awaiter, on its awaiter. So it has an awaiter. It calls await ready. Now, you read this is, are you ready? If we're ready, we return true. That means we're actually ready. So maybe we should not suspend. We're ready to do stuff. If we're not ready, yeah, then we should suspend. So typically, await ready, its implementation will be return false because we want to go for a suspension. Now, when you start using coroutines with asynchronous programming, then it might make sense not to suspend because the data is ready. And if the data is not ready, we're going to suspend. Await suspend, the second method, is called immediately after the coroutine is suspended. So the coroutine just has been suspended, and just before control is handed back to the caller, or to wherever the control will be handed over, just before that point, it calls await suspend. And it has a parameter, the handle of the coroutine that was just suspended. Again here, we have the option to neutralize the suspension and say, I changed my mind. Let's not suspend in the end after all. And then there is await resume. Await resume is called when the coroutine that has been suspended is resumed. And await resume can return a value. And that value is the return value of the co-await expression. So when you have co-await blah blah blah, you could say that's actually a function returning a value. That's this value that await resume would return. We already have seen two awaiters, suspend always and suspend never. Suspend always, its await ready says returns false. I'm not ready, so suspend. Suspend never says I'm ready. It returns true. It's never going to suspend. Those two awaiters, of course, also need an implementation of the two other methods. Await resume, which is empty implementation, and it returns void. So they don't do anything at suspension and resumption. The await resume and the await suspend. Okay. Now, let's see an application of that. When the coroutine yields us a value at suspension time, and for our radio station, we would like, when we resume the coroutine, we want to hand in a value ourselves and say, look, I have some new information for you, which I want you to use during the resumption. So in our radio station example, we will give a score to the song we have just heard. Now, when we get values out of the coroutine, that goes via the promise type. So this is most probably the most sane construct to use to pass in a value from our side back into the coroutine. So that means in our radio station class, we will have an extra member in the promise type. Our radio station class needs a method, let's call it score, which stores the value in there. And then the question is, how does the coroutine get this value out of the promise type? And so it becomes the return value of the co-yield call. That's being done by a custom awaiter. Let's inspect these things one by one. The API change, it's very easy. Radio station score, handle promise. There is a member in the score. Let's store it in there. Okay, that's easy. The value, the extra state. And now the coroutine itself, it calls co-yield. Co-yield or co-await, the return value of that thing, that's actually that value. So it comes out, we have the score, and we print it out. Now, there is still a few things missing. Yield value used to store the value and then said suspend always. In this case, we're creating my awaiter, my custom awaiter, and we're returning that. Okay, what would that need to do? Await resume can return a value. And that's the value that co-yield and that co-await expression yields. So that means in our case, we already were able to get that score value in a promise type. And if we have a handle, we are able to get to it. Now, so let's assume that the handle is a member of our awaiter, my awaiter. At constructor time, it's the null pointer. At await resume, let's assume we have that handle, We will see how we get it there. We say, give me your promise, give me that score, and that's what await resume returns. Great. One final piece of the puzzle is missing. How do we get that handle in there? Well, await suspend receives as an argument the handle of the coroutine that has just been suspended. So we can store it. And then await resume can use it. It's really that simple. So my awaiter, await ready. No, we're not ready. Always suspend. Await suspend, which happens just after the coroutine has been suspended and before control is handed back to the caller. The handle of the suspended coroutine comes in. We store it. And when we are resumed, we use it. And I think that's where I need to conclude. So what we have seen, there is some boilerplate to write. The promise type is where you can configure your coroutine and how it should behave and how you can pass values from the coroutine to you towards the coroutine. And we have seen one example of a waiter which allows you to also give extra power to coroutines. And with this, I'd like to thank you. If you want to see the 90-minute talk, you can find it on YouTube if you search for my name. I will put also a link to it on Discord. If you have any questions on Discord, you can ask them in the channel of this presentation and I will do my best to answer them. I thank you for your attention and enjoy the rest of the day. Bye bye.